Hey guys! As you probably already know, modern GPUs can do much more than just graphics. Basically, as the architecture of GPUs evolved into the beast of parallel processing power that we have today, it didn't take long for people to ask themselves, can we harness this power to do more than just render a few fancy triangles? Well, of course we can. But there is one problem that we need to overcome, and that is the programmable graphics pipeline. The familiar structure of going from the vertex shader down to the rasterizer and the fragment shader imposes too many restrictions on the implementation of general-purpose parallel algorithms. Out of this need rose the concept of general processing on the GPU, aka GPGPU. Different languages and frameworks were introduced as solutions to this problem, including CUDA by NVIDIA, OpenGL by Cronus, and the compute shader of OpenGL, which is also by Cronus. So today we will take a look at using the compute shader in order to create a particle system on the GPU. This particle system can be implemented in different ways, but fits very nicely to the capabilities of the compute shader. Now, if you find this stuff overwhelming and you don't know where to start in computer science, then I highly recommend checking out the sponsor of this video, which is Brilliant. Brilliant.org is a great place to start learning classical subjects in computer science and math, in addition to hot topics such as AI and data science. Brilliant provides dozens of courses and they keep adding more so you can always find something new to learn. The material is presented in a highly visual and engaging way, and the courses are full of quizzes and questions to make sure that you are actually absorbing everything. I always say that math is a core skill for 3D and game development, as well as programming in general. On Brilliant.org you can start from the basics of how to solve an equation and continue to geometry, linear algebra, calculus and more. Brilliant's method of teaching using visual elements, letting you interact with the material is not only effective for learning, it also makes everything much more fun. What's also great about Brilliant is that they give you a 30-day trial to check out everything on their platform, and if you want to go further, then you can get a 20% off an annual premium subscription. Simply go to brilliant.org/ogldev or click the link in the video description. Thank you Brilliant for sponsoring this video. The compute shader became part of OpenGL in version 4.3, which came out in 2012. The advantage of the compute shader over the older APIs that I've mentioned, CUDA and OpenGL, is that it is fully integrated into OpenGL, which makes it easier to render the results of the GPGPU algorithm, as we shall see in the particle system demo. The compute shader is part of an independent pipeline, which is separate from the graphics pipeline. The architecture of this compute pipeline is very simple. Boom, that's it! We have a single shader stage here. Unlike the fragment shader, which is executed as part of the interpolation of a triangle in the rasterizer, the compute shader is directly controlled by the application. Another difference compared to the graphics shaders is that the compute shader doesn't have user input and output attributes. Instead, it can read from and write to images and buffers at any offset. These resources can then be used to drive rendering. To understand the execution model of the compute shader, we need to introduce two concepts, the workgroup and the local size. The workgroup represents a single execution of the compute shader from the application point of view. So the application can execute one or more workgroups. To make it easier to map the number of workgroups to some concrete algorithm, the number of workgroups is actually organized as a three-dimensional space. For example, if you want to process an image with a width and height of 1000, you can set the workgroup size to be 1000 on the X, 1000 on the Y, and 1 on the Z. If you have more than one image, you can use the Z dimension as an index into an array of images. Alternatively, you can multiply the three dimensions together and have 1,000,000 on the X or more if you have multiple images, and 1 on the Y and Z. The bottom line is that you have a freedom of choice here in terms of how you organize the number of workgroups. So the number of workgroups is configured on the application side, but on the shader side we have the concept of a local size. This is also a three-dimensional space, which defines the actual number of shader invocations within a single workgroup. This means that the total number of invocations can be calculated by multiplying the 6 dimensions together, 3 from the workgroup and 3 from the local size. An important thing to remember is that workgroups run in parallel, and the invocations are also executed in parallel. This means that you can't assume anything about the order of execution between workgroups and invocations. The alternative to the image example that we saw is to have a single workgroup and set the x and y of the local size to 1000. In general, there are limitations to the workgroup size and the local size, and you can query them on each platform. However, the minimum of each of the 3 axes of the workgroup size is 64K, and in the case of the local size, 1K for the x and y and 64 for the x. This provides a very large room in terms of the size of the work, but it's probably a good practice to check against the maximum on the actual machine. At this point, you may be wondering about how you should partition the work between the workgroup size and the local size. One thing to consider is that you can communicate between invocations within the same workgroup using shared variables, but communication between different workgroups can cause deadlocks and data races and should probably be avoided. Now, if you're ready, we can take a look at our first compute shader. In this demo, the particles are simply going to move together. This is the entire compute shader. We begin by defining the input layout. The default size of each of the axes is 1, but we have to at least specify the x-axis. Next comes a shader storage buffer object, or SSBO. If you don't know what an SSBO is, then check out my programmable vertex pooling video, but in general, this buffer is going to serve as both the input and output of the compute shader. The layout of the buffer is specified as a C-like structure, which contains a vec4 array for the position of the particles. The size of the array is maintained by the system, so it is not hard-coded to a specific buffer. The main function begins by extracting the value in the X component of GL Global Invocation ID. This is one of 5 system-generated variables. It is a 3D vector which provides the position of the current shader invocation within the entire compute space. This means that if the local size is 10 and the workgroup size is 100, the range of this variable will be 1000. Other system-generated variables which you may find useful are GL_num workgroups, which tells you how many workgroups we have on each dimension, GL workgroup ID, which specifies our location on the workgroup level, and GL local invocation ID, which specifies our location on the shader level. As I said, GL global invocation ID takes into account both GL workgroup ID and GL local invocation ID. So we extract the X component from GL global invocation ID, and we use it as an index into the positions array. We fetch the current position, move it a bit, and then write it back into the same buffer. The fact that you can store the results of the shader back into the same buffer is very handy. To compile the compute shader, I'm going to use the same technique class as all my other shaders. The only difference is that we have to use the GL compute shader macro when compiling the shader. Other than that, compiling, attaching, and linking the program remains the same. To initialize the position of the particle, we are going to create a vector of vec4 elements. The user can specify the number of elements on each axis. We will organize the particles as a 3D cube, kind of like the Borg in Star Trek: The Next Generation, which was one of my favorite TV series in high school. The size of each face is 2, so the distance between particles is 2 divided by the number of particles. We can now go ahead and initialize the positions in a nested loop over the 3 axes. Very simple. We need to upload the positions to the GPU, so we create a buffer handle called GL-bind-buffer-base to initialize it as an SSBO, and then GL-buffer-data to update the SSBO with the contents of the position vector. We also need to render the position vector after it was processed by the compute shader, so we create and bind the VAO and set up the single vertex attribute as usual. During runtime, we need to execute the compute shader and then render the results. Execution of the compute shader is done using GL-dispatch-compute. Before calling this function, make sure to call GL-use-program on the program handle of the compute shader program. The function enable of the technique class is actually a wrapper of GL-use-program. GL-dispatch-compute takes a value for each workgroup dimension. This is another thing to consider. You can play with the workgroup size because this is just a function argument. But the local size is part of the shader, so changing it is less trivial. After GL-dispatch-compute, we have to wait for the compute shader to finish executing before we render the results. Remember that in general, the draw functions return very quickly and the execution takes place later on in the background. But here we have to wait, and we do that using a GL memory barrier. We now have the updated positions in our buffer object, and we can go ahead and render it as usual. Notice that in this case we are rendering points and not triangles. Let's see how to implement the particle system. At the core of the animation are 2 black holes with a strong gravitational force which is pulling the particles towards them. The black holes are moving about in a circle, and the demo renders them as 2 red points. Of course, you can turn off this visualization if you don't want to see them. It won't affect the movement of the particles. By the way, you can use the function GL-point-size in order to control the size of the points, which is very handy for cases like this. The gravity of the black hole is represented by a scalar floating point, so we have to multiply it by the vector from the particle to the black hole to get the force vector. Naturally, the force decreases as the particle moves away from the black hole. We will make the force inversely proportional to the distance between the particle and the black hole, so the formula to calculate the force of a single black hole on a particle is as follows. G represents gravity, which is a constant, and R is the vector between the 2 objects. Since we have multiple black holes, we actually need to sum up this formula over all of them to get the total force for each particle. We can now calculate the new particle position based on the total force which works on it. For this, we will use a simple Euler integrator to calculate the Newtonian equations of motion. First, we need the acceleration of the particle. The acceleration is the change in velocity over time. We will calculate it as the product of the force and the inverse mass of the particle. This makes the acceleration a function of the distance to the black hole. Next, we calculate the new position. We start from the old position, add the velocity multiplied by the delta time, and then half of the acceleration multiplied by the delta time raised to the power of 2. The velocity depends on the acceleration, so for the next execution of the compute shader, we will update the velocity by adding the product of the acceleration and the delta time to the old velocity. This means that we will need another buffer to maintain the velocities. We could pack the velocity together with the position into the same structure and then use a single buffer, but since we don't render the velocity, this will create gaps between the positions. Using a separate buffer for the velocity means that our rendering code doesn't need to change. Now let me say something about the delta time. you can update it before each execution of the compute shader as a uniform variable, but in this demo we will simply use a constant. We expect the demo to run at a fairly consistent frame rate, so the actual delta time is not that important. So this is the initial implementation of the particle system, and as you can see, over time some of the particles get away from the center of the scene and they never come back. Let's add a maximum distance from one of the black holes so that when a particle crosses that threshold, it is reset back to the origin. I think it makes the effect more interesting. And that's it for today. Remember that you can get a 20% off an annual premium subscription to Brilliant. Thank you for watching, and thanks again Brilliant for sponsoring this video.